All right, 7.5, properties of trapezoids and kites. All right, so far right here we have trapezoids. And basically, real quickly, a trapezoid is really just a triangle. Whoops. That has had the top cut off parallel to the base. So there you go. You have a trapezoid right there. You might have a right triangle. Cut the top off right there. And what do you have? You have a right trapezoid. So that's all a trapezoid is. Okay, it comes from triangles. So just so you see that. Now, we're going to find these angle measures. Let's see number 1. So we have parallel lines. We see that from the markings, and we have a transversal. So again, our old favorite, alternate interior angles. So angle 2, I'm going to start with angle 2 actually. That's going to be 60 degrees. Now, angle 1 and 2 are a linear pair. They form a straight line. Right here. That means angle 1 and angle 2 add up to 180. So 180 minus 60 is 120 degrees. All right? Now, if this is 120, all right, well, let's see what we have here. We have 120 plus 90, right there, and we have 60. If we add all those up, we get 170 degrees. Sorry, math is hard. Carry the 1, 270 degrees. So we've used up 270 out of 360 because, again, it's a quadrilateral, and all quadrilaterals, no matter what their shape, have 360 degrees in them. So 360 minus 270 is 90. So angle 3 is 90 degrees. All right? Angle 4. Well, again, we have parallel lines, and we have our good old transversal here. So right there, alternate interior angles, angle 4 is going to be also 45 degrees. Angle 5 is supplementary to that. So 180 minus 45, because they are a linear pair, that gives us 135 degrees. And for angle 6, we're going to do the same thing. I'm not going to show it. We know that angle 4 we said was 45. We know that angle 5 is 135. If we add up these 3 angles and subtract from 360, we will get 109 degrees. Just got to work your way through it. All right, show that ORST is a trapezoid. Then decide whether it is isosceles. Now remember, a trapezoid has only one pair of parallel sides. Okay? Only one pair. And if you think about it, again, since it comes from a triangle, like I said before, if you have a triangle, obviously the sides are not parallel, they're intersecting with each other. And then when you cut it off, and this side, this is parallel to the base, that's where you get the trapezoid. You get the 2 parallel sides. All right, and that's it. So basically, we need to show that OT is parallel to RS. Now, why did I pick those sides? Because you can see if I continued this line up and I continued this line up, what would I have? I'd have a triangle. So those are going to intersect eventually, so those are definitely not parallel. I just need to make sure the other 2 are parallel. So I'm just going to count. There's no reason to do y minus y over x minus x because I have the counting ability. So for RS, so the slope of RS is going to be up 1, right 2. And then the slope of OT is going to be up 2, right 4. Up 2, right 4, both positive, but that simplifies to 1/2. Those are the same. Now, common sense would tell you that the other 2 lines are not parallel, but if you want to prove it, it's pretty quick and easy. So, OR, well, that's just a straight vertical line, so that's undefined. or no slope. And again, ST you can clearly see is a slanted line. It has a slope, but what is it? Real quickly, up 1, up 2, left 1, left 2, so -1. So real quickly, we proved those two sides are not parallel. It did not take a lot of time, and it's good practice. Now, it did ask if it's isosceles, which means equal, congruent sides. So the 1 is really easy because it's straight up and down. So we're just going to count 1, 2, 3. So the measure of RO is 3. And then we do need to do the distance formula for ST. So the distance on ST is, again, I like to do this ahead of time before I plug my numbers in. So I'm going to do x minus x, so 2 minus 4, and well, 4 minus 2. All right, so that's the square root of -2 squared plus 2 squared. Well, -2 squared and 2 squared are the same thing. So that's the square root of 4 plus 4, the square root of 8, which is obviously not the same as 3 because the square root of 9 is 3. So not isosceles. All right, some more theorems. We always love theorems, more rules. The base angles theorem. If a trapezoid is isosceles, in other words, this side is equal to this side, then each of the base angles is congruent. All right? So this angle and this angle are congruent. Because if you think about it, if it came from an isosceles triangle, let's step back a little bit. Remember drawing lines, that means those are equal. Opposite angles are equal. So when we cut it off and make it into an isosceles trapezoid, that's why that works. Okay? And then consequently, if those two are equal, those two are going to be equal also because they're both bases. It says each pair of base angles. They're different numbers. You can see one's obtuse and one's acute, but both pairs are equal. Okay? Base angles converse. If a trapezoid has a pair of congruent base angles, then it's going to be isosceles trapezoid. So as long as you know, this and this are equal, then you know it's isosceles, just like we did with triangles. And the diagonals theorem. A trapezoid is isosceles if and only if the diagonals are congruent. Okay? Okay, the stone above the arch in the diagram is an isosceles trapezoid. Find the measures of K, M, N, and J. All right, well, this is a base and this is a base. So these two angles are going to be equal, so angle K is 85 degrees. Okay? Now, remember, we have consecutive angles are supplementary, so 180 minus 85 is 95. So that means angle M is 95, and base angles are congruent, so angle J is also 95 degrees. The mid-segment theorem. This is an interesting one. The mid-segment of a trapezoid is parallel to each base and half the sum of the bases. So to be a mid-segment, remember it has to go connect the midpoints. We see that from this and this. Okay? That means it's the midpoint. MN, okay, this line right here, MN, is half of AB plus DC. So if this was 5 and this was 7, 7 plus 5 is 12, making this 6. If this was 10 and this was 20, 20 plus 10 is 30. Half of that mn would be 15, and so forth. All right, so same idea here. Find mn. We know it's the midpoint because those two are equal and those two are equal. So all we have to do is do 12 plus 28. 8 plus 2 is 10. Carry the 1 this time. That's 40. And then divide by 2, 20 inches. Okay? Find the length of the mid-segment. All right, so what we need to do is find the measure of SV and TU. You might say, well, why don't we just do YZ? Because you can see this does not land at a certain number. It's a decimal. We don't know what it is, so we can't figure it out. We have to guess, and that's not what we do here. So we're going to do the distance twice. We're going to do the distance of TU, which quite simply is I'm going to do 8 minus 12, x is first, and then 10 minus 2. It doesn't really matter, but that's how I did it. So 8 minus 12 is negative 4, but again, that square is going to come positive, plus 10 minus 2 is 8 squared. So that's going to be the square root of 16 plus 64, which is the square root of 80. Okay? And then we're going to do the distance for OV, which is going to be 0 minus 2 squared plus 6 minus 2 squared. So that's negative 2 squared and 4 squared. So that's going to be negative 2 squared is 4, 4 squared is 16. That is the square root of 20. Now, technically, the way we're supposed to do this is to simplify the radicals. But you have not done that in a while. We haven't gotten into this course yet. So we're just going to change these into decimals and get an approximation. So the square root of 80 is about 8.9. And the square root of 20 is about 4.5. And these are both approximately. So we're going to do 8.9 plus 4.5 divided by 2. And that ends up being approximately 6.7. So YZ is approximately 6.7. All right, moving on to kites. If a quadrilateral is a kite, then its diagonals are perpendicular. All right. Now notice what happens here with a kite. We have these two pieces are equal and those two pieces are equal. That's what's different from a rhombus, where the diagonals are also perpendicular. All right, that's what makes it a kite. And then opposite angles theorem. If a quadrilateral is a kite, then exactly one pair of opposite angles are congruent. So these two, kind of like where the long sides and the short sides meet, those two angles are congruent. B and D are not. All right, find the measure of angle D. Well, first off, remember a quadrilateral has 360 degrees. We have 115 here and 73 here. How do we know it's a kite? These two are equal and those two are equal. So if I do 115 plus 73, that gives me 188. If I subtract 188 from 360, that gives me 172. Now that is what is to be used for both of those angles. So I need to divide by 2, and that gives me angle D is equal to 86 degrees. And our last example, what's the most specific name for this quadrilateral? Okay. Well, the diagonals bisect each other, okay? But we don't know anything about these. Do they look like 90? Yes, they do. Can we assume that? No, we cannot. All right? Do we know that this is intersecting a 90-degree angle in here? No, we do not. So all we can call this is a parallelogram. And that's it.